Good day, ladies and gentlemen. My name is Eldad Baat-Feidel, and I'm working in the Wide Bandgap Electronic Group in Ferdinand Braun Institute in Germany. I will speak today on Silvaco simulation tools assisting GaN-based power devices design and development. I will start with a brief introduction to Ferdinand Braun Institute in Berlin. I will give background on GaN-based power switching devices. We will look into examples for design and analysis using Silvaco simulation tools. There, we'll look at vertical FinFETs, channel conductance, and their geometrical and epitaxial design. We will look at vertical GaN devices drift region and edge termination design. And then we will look at lateral HFET devices with aluminum nitride buffer layer for high voltage switching. There, we will give insight to trapping and de-wrapping effects. Ferdinand Braun Institute is located in the southeast part of Berlin. We are a member of the Leibniz Association. Ferdinand Braun Institute is owned by the State of Berlin and the Federal Republic of Germany. It was founded in 1992. Our staff includes around 200 scientists and PhD students. We have partners and joint labs all across Germany. Our basic research program includes 3-5 electronics, photonics, integrated quantum technology, which are all supported by the 3-5 Semiconductor Technology Department. I work in the wide bandgap power electronics, which is closely working with the epitaxy and process technology department. In Ferdinand Braun Institute, we are working on semiconductors' full chain of supply, from materials to applications. Gallium nitride is relatively new wide bandgap semiconductor material. It has many merits for semiconductor electronic devices. It has high bulk mobility and may form in heterostructures two-dimensional electron gas with high channel mobility and high drift velocity, which give it superior conductance properties. Due to its large band gap, it has large breakdown electric field, which gives it superior blocking properties. GaN-based field effect transistors has two major topologies, lateral and vertical. Lateral HFET devices own superior transport properties due to the two-dimensional electron gas formation. They are planar, processed on a large wafer size, which can be integrated in silicon foundries. They are reaching technological and price maturity. Vertical FinFETs are strain-free homoepitaxy grown on freestanding GaN substrate. These allow epitaxial growth of thick drift regions. Therefore, they have reduced footprint with reduced specific on-state resistance, one order of magnitude lower compared to lateral HFETs. Since 2016, the research program of the Wide Bandgap Power Electronics in FBH focuses on vertical GaN-based switching transistors. We developed two types of gate module topologies, trench MOSFET and fin MOSFET. In parallel, we developed thick epitaxial drift region to support devices for 1200 volts rating. These devices could be manufactured on GaN substrate or on Sapphire for substrate transfer technology. For the next generation of lateral wide bandgap devices, aluminum nitride-based power transistors are developed. In these devices, binary compound aluminum nitride replaces doped GaN buffer layer and may replace the aluminum gallium nitride barrier layer. Aluminum nitride-based devices are grown in FBH on silicon carbide substrates or on aluminum nitride freestanding substrates. We will start with simulation examples of vertical GaN-based devices. GaN-based vertical fin MOSFETs are one of the most promising concepts for power switching application. In the schematic cross-section, the principal concept of the device is shown. The source electrode is located on the top side of the fin. The gate electrodes are located on both sides of the fins. The gate metal is electrically insulated with dielectric material such as aluminum oxide, and the drain is located on the back side of the wafer. The FIN MOSFET concept has many advantages. FIN MOSFET has simplified N-type GaN epitaxial layers, and no P-type layers are required. In on-state, the channel transport is based on electrons accumulation, and FIN MOSFETs enable very compact design with very large gate periphery per active area. Our first example, we modeled the on-state conductance in GaN-based FIN MOSFETs. For the simulation, we used the following physical models: the concentration-dependent Shockley-Read-Hall recombination, Auger recombination, Fermi-Dirac carrier statistics, and lattice heating. For mobility, nitride field-dependent model for electrons was chosen. To simplify the numerical solution and to improve the solution convergence, electrons as single carrier is used. The simulation fitting for the experimental measured data needs optimization of the following parameters: the interface charge in gate insulator, channel interface, the oxide permittivity to compensate other charges, and the channel mobility. The on-state conductance simulation is fitted now to the experimental data. On the left side, we can see the transistor transfer characteristics, the off-state at 0 volt for normally off operation, the positive threshold voltage, and the output current at on-state. On the right side, the device electron concentration cross-section under off-state and on-state is shown. At off-state, the gate voltage is 0 volt, and the fin and the drift layer top side are depleted. At on-state, the gate voltage is 5 volts, and the fin is conducting through the drift region to the bottom side drain. After matching the simulation output to experimental measurements, we can use the simulation to predict the influence of geometrical dimensions and material properties on the output characteristics. Here we give example for fin geometry variations and the drift layer dimensions and composition. The influence of the geometrical variations is important for understanding variation caused by the manufacturing process, and the drift layer dimensions and composition variations are essential for the layer design towards 1200 volts blocking strength. Initially, we examined the influence of the drift region doping concentration on the output characteristics. We observed that, on one hand, the normally off characteristics in the threshold voltage are not affected by the drift region concentration. On the other hand, we see a strong reduction of the output current with reduction of the drift region doping concentration. Then, we examine the influence of the drift layer thickness on the output characteristics. Here again, we observe that the normally off characteristics and the threshold voltage are not affected by the drift region thickness. But we see a strong reduction of the output current with the increase of the drift region thickness. It is clear to see that the drift region resistance is a major contributor to the on-state resistance. Next, we explore the influence of the fin geometry on the output characteristics. We would like to know how the fin height affects the channel conductance. The fin height has large influence on the manufacturing process parameters, such as the required lithography mask technology, the GaN recess depth etching, and the self-aligned planarization process. From the simulation, it is evident that the fin height has small influence on the output current and has small influence on the threshold voltage. This information allows us large flexibility in the manufacturing process. Similarly, we would like to know how the fin width affects the channel conductance. The fin width has similar influence on the manufacturing process parameters as well. The required lithography mask technology. Do we need e-beam lithography or optical lithography? The GaN recess etching process and the self-aligned polarization process. From the simulation, it is evident that the fin width has small influence on the maximum output current and has a significant influence on the threshold voltage. The wider the fin, the more negative is the threshold voltage. Again, this information allows us large flexibility in the manufacturing process. For the second simulation example, we model the drift region and the edge termination in vertical GaN devices. To characterize a drift region epitaxial layer, we choose GaN-based Schottky barrier diode. We would like to assess the reverse blocking strength of the drift region with the different drift region doping concentration and the different edge termination geometries. For the simulation, we use the following physical models. For mobility, the nitride field-dependent GaN-SAT model for electrons as chosen. We use the Zelber impact ionization model for carrier generation. It simulates avalanche breakdown. Here, since we simulate off-state conditions, no large power is dissipated, therefore thermal effects were neglected. We simulated the output current under reverse bias condition until compliance of 0.1 milliamp. This example, we would like to understand the influence of the following variations on the device breakdown. The drift region net carrier concentration between 1 times 10 to the 15 to 5 times 10 to the 17 per cubic centimeter. The edge length, which is the implanted top surface width from the active area to the edge termination, and the implanted top surface p-type doping concentration up to p-type doping concentration of 3 times 10 to the 17 per cubic centimeter. On the left side picture, we can see the resulting reverse bias blocking characteristics as function of the drift region doping concentration. We clearly observe impact ionization avalanche characteristics. In addition, the blocking strength increases with the reduction of the doping concentration. Below 10 times 10 to the 16 per cubic centimeter, the breakdown reached saturation close to the theoretical average value of 3 megavolt per centimeter. On the right side picture, we can see the resulting reverse blocking characteristics as function of the edge surface implanted region p-type doping concentration. Here as well, the blocking strength increases with the p-type doping concentration. For better understanding the resulting reverse blocking characteristics, we look into the device cross-section. Here we can analyze the device electric field strength under breakdown conditions. For low edge termination doping concentration, high electric field is concentrated at the edge of the active area. This leads to early breakdown conditions. With increase of the edge termination doping concentration, the electric field is more equally distributed along the edge. This reduces the electrical field peak at the active area and result in an enhancement blocking strength. The simulation results may now be compared to theoretical analytical model. Maeda showed the dependence between the breakdown voltage of one-dimensional diode for GaN to drift region doping concentration. We can see that there is very good agreement between the simulation results and the analytical model. To qualify the drift region epitaxial layers, we manufactured in FBH vertical GaN diodes on sapphire substrates. Here we can see diode reverse bias characterization as function of the temperature. Clear avalanche behavior could be seen. Here we can compare both the experimental results and the simulation results to the theoretical analytical model. Here, we choose simulated structure similar to the manufactured diodes with 5 micron thick drift region, 5 micron wide edge termination, and 10 to the 17 per cubic centimeter p-type edge doping. Very good agreement between the simulation analytical model and the experimental measurement is observed. The right bottom figures show the experimental results power figure of merit. It shows the state-of-the-art results for drift region and edge termination design of vertical GaN diodes on sapphire substrates. We can continue now with simulation and analysis example for lateral GaN HFET device. In this new generation lateral HFET device, aluminum nitride compound replaces the commonly used doped GaN as buffer layer. Aluminum nitride is a binary ultra-wide bandgap compound. It has high breakdown strength, high polarization, which leads to high two-dimensional electron gas concentration, and enhanced conductivity. It has high thermal conductivity, and it is intrinsically insulating. Therefore, aluminum nitride buffer leads to high lateral and high vertical breakdown strengths. Since aluminum nitride does not require compensation doping, better trade-off between breakdown strengths and dispersion is expected. When the aluminum nitride GaN HFET devices were characterized under dynamic condition, we discovered a unique behavior. At first, above 275 volts, strong increase of the dynamic on-state resistance up to 400% is observed. Then, between 400 volts to 550, it decreases down to a level of 50%. We could learn from this behavior that two separate trapping mechanisms exist in these devices. Here, our simulation task was to get insight to the mechanism dominating the dynamic on-state resistance. For this example, we modeled the off-state characteristics of aluminum nitride GaN AlGaN HFET. For the simulation, we used the following physical models: the concentration-dependent Shockley-Reed-Hall recombination, Auger recombination, Fermi-Dirac carrier statistics, nitride field-dependent GaN-SAT mobility model, the Selb-Herer impact ionization model for carrier generation, polarization and strain calculation for two-dimensional electron gas simulation, the simulation fitting to the experimental measurements needed parameters optimization, polarization and strain scaling parameters, and the channel mobility. We can look now at the device electric field strength cross-section under different drain bias conditions. The parameters values are extracted on the GaN channel aluminum nitride buffer cut line. At lower drain bias, the electrical field peak is located under the gate. For high drain bias, a large electrical field peak rises on the drain side. Under the same drain bias conditions, we can look now at the device electron density cross-section. We can now observe electron concentration increase with the drain bias. Such increase gives yield to increase of electron trapping at defects that result in dynamic R-on increase. At high drain bias, we can observe a strong increase of electron concentration on the drain side. We can continue with our investigation by looking at the impact ionization rate cross-section under the same bias conditions. Under high field condition, electrons and holes are generated due to the impact ionization. Under high drain bias conditions, high generation rate is observed on the drain side. As a result of high impact ionization rate, large number of holes are generated under high bias conditions on the drain side. Holes generated by the impact ionization on the drain side accumulate on the GaN channel aluminum nitride buffer interface. Conduction current path from the drain to the gate source is formed. Looking into the carrier's concentration balance at high drain voltages, we can see the following. In the lower drain voltage regime, the electrons are the majority carriers. With the increase of the impact ionization generation, the hole concentration increases and suppresses the electron concentration. Electron majority at the GaN aluminum nitride interface leads to strong trapping. A hole majority in the interface gives a path for detrapping. For comparison, we have looked on simulation results of similar device with conventional carbon-doped GaN buffer structure. In carbon-doped GaN buffer structure, holes are also created by impact ionization. Holes may move vertically towards the grounded substrate, but holes are not stopped by the valence band offset at the channel buffer interface. Therefore, we have identified that Hall accumulation layer is unique to the aluminum nitride buffer structure. We can now summarize our work and studies with Silvaco simulation tools. For GaN-based vertical devices, we have used the simulation tools to predict the FinFET conductivity in relations to the geometrical dimensions and the epitaxial layer composition. We predicted and maximized the vertical blocking strength as function of the drift region properties and the edge termination design. We optimized the drift region properties for low on-state resistance. In this way, we demonstrated experimentally maximum power figure of merit. And for lateral aluminum nitride GaN AlGaN devices, we have used the simulations to give insight to dynamic on-state resistance anomaly due to trapping and detrapping effects. I would like to thank you for your attention, and to my colleagues Enrico Brusatera and Oliver Hilt for our teamwork. The work shown in this presentation was done under several projects: Pioneer GaN, Yes We GaN, GaN for AP, Hover GaN, AlPower, Lightbahn, and the Research Fab Microelectronic Germany. Please do not hesitate to contact me for any of your questions.